Hello, and today's video on 6.6 is on surface area. So we've looked at volumes of figures as we revolve them around a axis. We've looked at arc length. This kind of combines both of them. And if you think about it, suppose we have some oddly shaped, say, package or something like that, right? And we take this package, right? Maybe it looks like that. All right. This, like this. Boom. Could be a vase, could be a package. And we want to calculate the surface area of this particular figure. Well, unlike basic geometric shapes like cones and cylinders and everything else, we don't have a formula for surface area. When we talk about surface area for a curve revolved around an axis, we're only talking about the curve portion of the surface area. I want you to keep that in mind. The base, this is hollow, okay? So on both sides, you are only looking at from here to here and that revolution around. Okay, so we're not looking at the area of the base to be included in that surface area or the area of the other base to be included in that surface area. So that's an important concept to understand. This has a lot of value in everything from basic packaging design and product design, putting labels on things to determine, you'll need to know the surface area, from aerodynamics and the surface area of airplane wings down to surface area of something like a cell membrane. So lots of applications. To do this, let's go back for a second. I am not going to take you through the full evolution of how we're going to get this formula. If you would like to see the full evolution, I will guide you to go to pages, everything from 457 to 460 in our text. It is unlike the others, such as volume and arc length. It is way more detailed. So if you want to do that, you can look there. I'm just going to kind of show you a overall general concept of where this integral is going to come from, because I think understanding that general concept is really going to help you, right, memorize it. Because ultimately, when you see this formula, you have to memorize it. So this idea, again, goes back to our Riemann sums, but our Riemann sums in this case are like these bands. So this is our A value. And then I'm going to make a rather large band right now. And there's our B value. The band is here, right? And then up through there. That's your band. And what we're going to do is take, as you can imagine, infinitely many of these bands until they're so tiny. All right, just think of a rubber band around some sort of a vase or something like that. So that's ultimately what we're going to do. But how do we get the information from this particular band? That you can kind of go back to, if you just think of a very basic figure, let's go back to our cone, right? Suppose we have a cone revolved around our axis, right? Again, it's open. You can put your hand right through it, all right? So this cone has a slant height. L represents what we call slant height, okay? And as you notice, that slant height, of course, is going to be really important because it's that slant height, whatever that particular length is, that's going all around. Well, that's also something we just did in the last section, which is, right, length of a curve. So if we already know the length of the curve, and again, we're looking at bands, so let's just look at the band here from, say, A to B. We look at just this band. Well, you can get the slant height because we did that in the last section. It's basically the arc length of a curve. In this case, our curve just happens to be the side of a cone. And we already know that to be 1 plus f prime of x squared dx. But unlike what we did in the last section with arc length, we don't want just one simple line. We want to revolve it around, but we're not interested in anything on the inside. So when we did volume, we were interested in everything on the inside. So we use the idea of a slice, right, a disc, and we use the idea of area because area will give us everything that's inside, and we took all those infinitely many discs to get the volume, or shells. We also did it with shells. For this one, think about it. Well, you don't, because the base is open, it's not area we're looking at, it's circumference, right? So all we really need to do then is take our circumference times our arc length. Now let's talk about the radius. At any given point, and by the way, when you take this little section, it's called a frustum. Interesting little word. Frustum, we're taking one single frustum, right? At any given point, the radius is just going to be our f of x value. So the radius, so the circumference is 2 pi f of x. And we come over here, we are going to take infinitely many of these, and we already know if we sum infinitely many, if we sum n of them and take n, the limit as of that sum as n goes to infinity, we are doing an integral. And that integral is simply the circumference times the arc length. That's all it ends up being. So for the circumference, 2 pi f of x, I'm going to pull the 2 pi out here from A to B. So I have f of x times the radical 1 plus f prime of x dx. So again, you can go through pages 457 to 460, and it'll go through that summation and taking that summation limit to infinity. It will also go in more detail with the cone and how that 1 plus f prime of x comes to be, and all the other pieces as well. But you're good just getting the formula down. But feel free, if you'd like more information, to go through those sections in the textbook. That's it. And that is our formula. So, you know, volume, when you did discs or even washers, you used area of a circle, right? When we moved to shell, it was more of the surface area of that cylinder. We used the cylinder. As we moved to arc length, it was essentially Pythagorean theorem, which is where you get the 1 plus f prime squared from, the square root of that. And now surface area is kind of putting together. If you already know your arc length and you know the circumference of a circle, you're just putting those two pieces together to get this particular formula. Because yes, fortunately, you will need to memorize these formulas when it comes time for the test. And this is, of course, if we are revolving about the x-axis. You all know by now we can make a slight change to this formula. I'll use G if we want to revolve around use G. I got to stick with G. There we go. And this is about the y-axis. So again, I'm just giving you enough background to help you memorize the formula. Let's do some examples. I want to start with one. It's a little bit easier. And then I'm going to move to one that appears difficult, but ultimately really isn't. So again, I will pick even problems from the textbook. I'm purposely not choosing the ones that are already worked out in your textbook, so that gives you additional resources. Those problems you'll also find them in our notes in Canvas. I'm not going to do the odd problems from the textbook because those you have fully worked out in the Student Solution Manual, so that gives you additional practice as well. So number 10 from 6.6 in our textbook is going to give us a figure of y equals x cubed for x between 0 and 1. And we're going to go about the x-axis. Always double check, make sure your equation matches the revolution axis. So we're going about the x-axis, which means our equation must be solved for y, and it is. So we're good to go ahead and just get started with this one. So that gives us surface area equals 2 pi integral from 0 to 1. And remember, we're using the x one, which is right there. I have to move it up a little. Of x cubed radical. Ooh. So one of the things you also want to do is we need y prime, right? We need our derivative. Don't forget to take your derivative each time. That's just 3x squared. 1 plus, and of course, 3x squared, because in the formula, which I forgot to put on each of these. Sorry, go back. Oh my gosh. Hopefully you were all thinking you didn't square it, even though it's squared for arc length. It must be squared for surface area too. I did not mean to confuse anybody. So please make sure they are squared. It is the exact arc length formula times the circumference of the base. Okay. All right, so when we square that, we get 9x to the 4th dx. This is a nice. Here's what's these problems almost set you up perfectly for u substitution because you can kind of see right here if we let u be 1 plus 9x to the 4th du is 36x cubed dx. Well, look at that. I already got the dx. I already got the x cubed. So it literally, having the function out front almost does set you up perfectly for a u substitution problem. Oh, but we don't have the 36. So we can add the 36 as long as we go ahead and get rid of it on the other side. Okay, don't forget to do that. So this is your basic u sub problem, which is then, oh, don't forget the last piece. Our limits, 1, if you were to plug 1 into u, would be 1 plus 9 goes to a 10. The upper limit from 1 goes to 10. And the lower limit of 0, when I plug it in here, 1 plus 0 goes to 1. If you go ahead and make those changes, it's just going to make the rest of the problem so much easier. So that's pi over 18. Let's go from 1 to 10. The 36x cubed dx, all of that, I'll circle it, 36x cubed dx simply becomes du. And we have radical u du. Again, because we changed the limits, we no longer have to go back. We can just finish the problem out with our u's. All right. So pi over 18. That's u to the 1/2, which we've done a whole bunch of times by now, which is u to the 3/2 times 2 over 3. And that's from 1 to 10. I'm going to move the 2/3 and the pi over 18 together. And pi over 18 times 2/3 becomes pi over 27, I believe. Yeah, the 2 cancels and 9 times 3 is 27. And then go ahead and take u from 1 to 10. So it's pi over 27. 10 to the 3/2. Think about that real quick. 10 to the 3/2 means the square root of 10 cubed, which is a 10 squared times 10, so it's 10 radical 10. So it's 10 radical 10 minus 1.